Okay, so hello everyone and welcome to phyloseminar.org. Sorry about the technical hiccups. So now we are having a three-talk series on viral phylodynamics. So this includes Erik Volz, who's going to be speaking today, and then Matthew Hall from Edinburgh, and David Rasmussen from ETH. So today, this is sort of co-organized by Trevor, who's going to be introducing Erik.
Yeah, it's great to have Erik here today. He did his PhD at Cornell, postdoc at UCSD, but I met him when he was at Michigan doing a faculty position. And there he did some of the very foundational work on connecting the coalescent with epidemiology. So basically trying to infer the number of infections through time using coalescent models, showing that it's not just counting up the number of infected individuals to give you an effective population size. Has since done really great work on structured coalescent, and it's just really foundational and great. Since then, he's moved to Imperial College, London, and joined the team of epidemiologists there. He'll be talking about Ebola, I believe, and I'm looking forward to it.
Great.
Yeah, thank you, Trevor. So I'm very honored to be contributing to the seminar series. I've seen quite a few phyloseminars, and I'm really happy to be making my contribution to the series. So thank you, Erik and Trevor, for inviting me to give this talk. Please give me a thumbs up so that I know you're seeing the slides.
Yeah, looking great.
All right, good. So as you can see, that there was a fairly late change in the title to the talk. Rather than talking about infectious disease epidemics in general, I'm going to be talking about Ebola in particular. There are a couple of reasons for that. Firstly, people are very interested in Ebola, and that's good at focusing people's attention. But also, as I've been working on Ebola for the past month, I've found that it's actually very good for educational purposes and demonstrations. Because the epidemic itself is actually relatively simple. We can use fairly simple models to understand the Ebola epidemic, at least currently, because it's really just growing exponentially. And also the sample sizes are quite small. So this talk, I'm gonna try something a little bit different. This talk is basically an Ebola sandwich. It's going to start with Ebola, it's going to end with Ebola, and then all of the educational content about population genetics of infectious diseases is going to be in the middle. So I'm going to start by reviewing what we currently know about the state of the Ebola epidemic in Western Africa. I'm actually going to do things a bit backwards. I'm going to show you some of my results from looking at the currently publicly available sequences. Then I'm going to talk more about the general theory for how we make these inferences, and then I'll return with some final results about Ebola at the end. Okay, so as of the last report released by the World Health Organization on 26 September, there were 6,500 confirmed probable and suspected cases and more than 3,000 deaths. The epidemic is concentrated in Liberia, Guinea, and Sierra Leone. There have been spillover events into Nigeria and Senegal, and surprisingly Texas. A few days ago, the first diagnosis of Ebola outside of Western Africa occurred in Texas. And I've talked to some people about that, and it turns out there's actually a large Liberian community in Texas, as well as New Hampshire. So perhaps we'll also see some cases pop up in New Hampshire. Incidence has grown exponentially at a fairly steady rate. Current intervention efforts haven't really had much of an impact, with the possible exception of Guinea, where there's some evidence that incidence is starting to decrease. Ebola infection is very deadly. The case fatality rate is estimated as at 71% approximately, according to latest estimates from the WHO Ebola response team. The WHO, by the way, have an excellent recent publication in the New England Journal where they present estimates of incidence, serial intervals, incubation periods, and so on. So it really summarizes, to the best of our knowledge, the current state of the epidemic. And in this paper, they estimated R0 in Sierra Leone, for particular, as around 2. And this is based on cases reported to the WHO by the local health systems. So this figure shows incidence of infection through time, and the bottom figure shows predicted incidence through time for Sierra Leone in particular. The projections, which I view as optimistic, are that in a month's time, on November 2nd, there will be about 6,000 infections in Guinea, about 10,000 in Liberia, and about 5,000 in Sierra Leone. So we will have passed the 20,000 mark in a month's time. The reason these projections are optimistic is that it's very likely that many cases aren't being reported. And it's very hard to estimate what the reporting is. Actually, one of the more interesting applications of genetic sequence data is that we might be able to get a rough estimate of what the reporting rate is. So the analysis I'm going to present is based on the only large publicly available data set of Ebola virus sequences. This comes from a study by Geyer and co-authors published this past month in Science. In this study, they sampled 78 patients in Sierra Leone. They did whole genome deep sequencing. So there are about 18 kilobases in the Ebola virus genome. And Andrew Rambo at the University of Edinburgh estimated timestamp using BEAST. This figure shows how the samples were collected through time. So the sampling is quite far from random, actually. The black points show the cumulative cases reported by WHO, and the red triangles show the samples. So it looks like the team in charge of collecting the samples sort of collected them at a constant rate through time, and then there's a big surge at the end. So in the original analysis by Geyer et al., they were able to estimate a substitution rate of about on the order of 1 per 10,000 sites per year. And they found that the substitution rate within the current Ebola epidemic is about twice as high, which is possibly a consequence of purifying selection and adaptation to a new host species. If you root the Ebola virus phylogeny on the oldest Ebola clade from 1976, you get a very nice linear correspondence in root-to-tip divergence versus time. The figure in the bottom right shows the timestamp phylogeny estimated by Andrew Rambo, and the distributions show the credible intervals for the times of common ancestry. So for the Sierra Leone clade, it looks like there is just a single introduction from which all of the Sierra Leone samples are descended, probably from Guinea, and the common ancestor of the Sierra Leone clade is somewhere in the vicinity of April to early May. Okay, so what I've done is a phylodynamic analysis of the timestamp phylogenies estimated by Andrew Rambo. And before I talk about what I've done, it behooves me to define phylodynamics. And I'm also lucky that I'm the first speaker in this series, so I get to say really whatever I want about phylodynamics. But this is a term that was defined by Brian Grenfell in a 2004 paper. The original definition was meant to be a synthesis of population genetics, mathematical epidemiology, and mathematical immunology. And I've printed mathematical immunology in small typeface for a good reason, and that is this term phylodynamics has been co-opted by many authors, and it's sometimes been used in many different ways. And very frequently, this immunological aspect of phylodynamics falls by the wayside. And indeed, in the analysis I'm going to present, there isn't a very big immunological component. It does rear its head occasionally, but primarily I'm going to be talking about the problem of fitting models for mathematical epidemiology to phylogenies. So, but bear in mind, in the original definition of phylodynamics, there is this idea of linking everything to mathematical immunology as well. All right, so the main benefits of a phylodynamic analysis is that it gives us an almost independent perspective on things that are really helpful for epidemiological surveillance. So we can generate independent estimates of the number of infections through time, so independent of the case reporting by WHO. We can generate independent of the epidemic growth rate and the reproduction number. And in the case of Sierra Leone in particular, there's actually quite a lot of confusion about what the reproduction number is. In the past month and a half, there have been 5 studies published that report R0 for Sierra Leone, and they follow a massive range from 1.2 to 8.3, and most of the estimates cluster around 2. So it would be very nice if we can use the genetic data to say which of those estimates is most credible. There are also a few things I'll talk about, especially towards the end of the presentation, that are best learned from genetic data. There are things that we can't tell from case reporting and from contact tracing that we actually can tell from genetic data. All right, so I'm going to start the presentation with actually one of the main results. This shows the estimated number of cumulative infections through time, estimated from the timestamp phylogenies. The shaded region shows the 95% credible interval. The black line shows the median estimate, and the black points show the cumulative infections reported by WHO. And those cumulative infections weren't used for fitting the model. So we can see that the estimates that we get from the phylodynamic analysis are really consistent with the case reporting by WHO. In general, the estimated number of infections from the genetics is a little bit higher than the case reporting, and that might actually be true. That might reflect a little bit of underreporting in the WHO data. Although we also have to point out that the credible intervals are extremely wide. And that's partly a consequence of the small sample size, and it's partly a consequence of there's a great deal of uncertainty in the phylogenies, in both the topology and in the branch lengths.
So can you which was observed and which was not observed? The black lines were used for fitting the model, right? Or the black dots?
The black dots were not used for fitting the model. That is the cumulative infections reported by the World Health Organization.
Oh, okay. So I see. So what you're using is the genetic data and the trees, and then predicting the number of cases.
Yep, exactly right. And so that the purpose of this figure is really to show that what we get from the genetic data is totally consistent with the actual cases reported by WHO.
So there are no tips on the tree that are earlier than like May 20th or whatever that I'm seeing, where the black dots start hitting 0.
That's right. Yeah, the samples were from May through June.
Okay.
And, I didn't extrapolate beyond the last time of sampling either.
Mm-hmm. So could it be that those early dates, these May dates, those are infections that are not in Sierra Leone, that the tree kind of traces back to their historical location somewhere else?
You can't rule that out. I mean, it could have actually, the lineage may have passed back and forth across borders multiple times before generating the Sierra Leone clade. Anecdotally, there's a story about a funeral in Sierra Leone, which was a super spreading event, where multiple people laid their hands on an Ebola victim. And it's thought that that triggered a lot of the infections, that basically all of the Sierra Leone samples are descended from that.
Wow.
But yeah, it is indeed possible that part of this epidemic history in early May took place outside of Sierra Leone. Okay, we also get estimates of the reproduction number. Unfortunately, we can't quite pin this down because the reproduction number depends on the incubation period. And the incubation period until recently wasn't known for the epidemic in Western Africa. So estimates in the literature for previous Ebola epidemics range from around 5 days to around 12 days. And we repeated our analysis with both periods. So that gives us a lower bound and an upper bound on the plausible or not values. Now the latest estimate from the WHO, which is probably a very good estimate, is that the incubation period is between 9.5 and 11.5 days. So that suggests that R naught, if we were to redo this analysis, would probably be a little over 3. Okay, so I'll return to Ebola at the end, but now I'm really going to talk about the theory that underlies those estimates. Okay, so there are actually a lot of different approaches to doing phylodynamic inference, and I really only have time in this talk to talk about the methods that I work on myself, and that is coalescent models, and not even coalescent models in general, but a particular type of coalescent model. So demographic inference with coalescent models has been done for a very long time. It's a very popular approach is to use, for example, the skyline estimator of effective population size. There are also a variety of parametric growth models like exponential and logistic that are often used. Recently, for about the past 5 years, we've been developing coalescent models that are derived explicitly from epidemiological models. And that's what I'll present. But before I do that, I want to point out that there's actually a big diversity of approaches now. There are increasing numbers of people working in the field. And the approaches I present aren't necessarily the only ones available. So, for example, there's feature matching approaches. There's a large group here at Imperial College that works on this, comparing simulated genealogies to observed genealogies. An interesting alternative to coalescent models are the birth-death sampling models, especially developed by Tanja Stadler and Zurich. And then I would also classify this as a type of phylodynamic inference, that there are models based on inferring who infected whom. And these methods are especially appropriate when sampling a very large fraction of the population and when the sample size isn't too large. So, for example, nosocomial infections. So I'm also going to start out by addressing the question of why we need a different coalescent model in the first place. So why aren't the skyline estimators good enough? And the short answer is that the existing coalescent models don't account for the fact that incidence and prevalence of infection changes very rapidly through time in a nonlinear fashion. And that introduces a very complicated relationship between the effective population size that you can estimate with a skyline and with the true number of infected individuals, IFT. And for those not up on epidemiological terminology, by incidence, which I'll use many times throughout the rest of the talk, I mean new infections per unit time, and by prevalence, I mean the proportion of the population infected. Okay, and for those not familiar with coalescent models, I'll also give a quick introduction. So coalescent models are mathematical models for genealogies, and the most simple coalescent model defines the rates that different events can happen, especially the rate that a coalescent event can happen. So, for example, the rate that branch 1 and 2 will coalesce at a common ancestor. The time between consecutive coalescent events is called the internode interval, and the most simple coalescent models connect the observed internode intervals in a genealogy to a model of the demographic process. In more complex coalescent models that we'll get to later on, other events can happen. So, for example, you might have a structured coalescent model where each lineage in a genealogy can belong to a different deme, and then the coalescent model defines the rates that a lineage will move from one deme to another. So I'm going to start by talking about the simple instruction models, where all we have to worry about is the time between consecutive coalescent events, and then in the next portion I'll talk about structured models. So this figure is taken from Rosenberg's and Nordberg's review of Coalescent in Nature Reviews. And it shows how the original Kieman coalescent model was derived for a very simple demographic process known as the Wright-Fisher model. In the Wright-Fisher process, there are discrete generations. And the number of offspring that a single individual will have in the following generation follows a binomial distribution. So a consequence of that is that if you pick a gene copy in a given generation and ask who is most likely to be the ancestor in the preceding generation, the answer is that the ancestor would be drawn uniformly at random from the preceding generation. And what Kingman did back in 1980 was derive the rates that lineages will coalesce under this very simple demographic process. And he also generalized it to situations where the population size can change between generations. So the way you do that is to, first of all, calculate the probability that if you sample little n individuals in a given generation, with a population size big N, that they will all have distinct ancestors in the preceding generation. And this first equation gives that calculation, and that motivates the definition of the coalescent rate. So the coalescent rate is the rate that any two lineages that are extant at some time in the past will coalesce and have a common ancestor. And that's simply the number of lineages A, choose 2, and is inversely proportional to the effective population size. So the definition of effective population size that I'm using here is simply the population size that gives you the coalescent rate that's observed in the given genealogy. And that's basically the definition of effective population size used by the skyline estimator. The skyline estimator is the maximum likelihood population size within each observed internode interval for a given genealogy. Okay. So before I talk about how we can relate effective size to epidemics, I'm going to go through a few slides that introduce the basics of mathematical modeling of infectious diseases, because I think most of the people tuned in population genetics and phylogenetics. So I'll describe one of the most simple epidemic models, which is known as the Kermick-McKendrick susceptible infected recovered model. According to this model, every individual in the population starts out as susceptible. They become infected, and when they're infected, they can infect others. And then they become recovered or removed from the population. And according to the most simple model, they cannot become susceptible again after that. So Kermick and McKendrick derived the following two differential equations. This describes the number of susceptible individuals through time and the number of infected through time. And this was derived under the mass action principle. So the idea here is that the incidence of infection is proportional to the product of the number of infected and the number of susceptible at a given time point. And beta is the transmission rate, and gamma is the recovery rate. So there are really 4 parameters in this model, beta and gamma, as well as the population size n. And usually there's also some parameter for the initial conditions. That might take the form of the time when a single infected individual into a population, or maybe the number of infections that were introduced at a particular time point. Okay, so this is sort of a very simple example of an SIR epidemic, where blue is the number susceptible, red is the number recovered, and green is the number of infected through time. And SIR epidemics progress through 3 phases. There's a period of exponential growth, then there's a period of saturation as more of the population gains immunity, and then extinction of the epidemic is in state in the simple SIR model. Although if there's recovery to a susceptible state or birth into the susceptible state, you can get more interesting things like oscillating dynamics or convergence to a steady state. And when epidemiologists work with these models, they're usually interested in calculating a few summary statistics. These statistics are sort of useful for characterizing an epidemic. So the first, of course, is the reproduction number. This is usually defined as the expected number of transmissions made by a single infected individual if introduced into an otherwise susceptible population. And for the Kermick-McKendrick model, that's just the transmission rate over the recovery rate. And it's actually very easy to derive this. I think the easiest way to see this is to view transmission and recovery as competing Poisson processes, in which case the mean number of events is just one rate over the other, and the number of events would follow a geometric distribution. And very similar calculations pop up a lot in population genetics as well. So for example, the number of mutations along a branch might also follow a geometric distribution. Epidemiologists also derive things like the final epidemic size as a function of R naught, and that can be found by finding the roots of this equation. And the probability that an epidemic will happen following the introduction of a single infected individual into a susceptible population, which is also a function of R naught. So a lot of things can follow from R naught, provided you're actually able to calculate it. So suppose we sequence the pathogen and reconstruct a time-stamped phylogeny. It would be tempting to say that the affected population size will be equal or proportional to the number of affected individuals. Unfortunately, that's not right. And the basic reason is that this estimate, the skyline estimate in particular of effective size, is based on a demographic process. Population size may change through time. So if the birth rate and the generation interval are not constant, this simple relationship between the number of infected hosts and effective size breaks down. So I will actually show you an explicit solution for the effective size for the SAR model. But first I need to get you to think about a slightly different process. So we can't get very far by thinking about differential equations. If we're going to think about population genetics, we have to think about an individual level stochastic process. So the model you should actually have in the back of your mind is one where an infected individual will generate another infection with the rate beta S over n. And also an infected individual will be removed from the population at a per capita rate gamma. So this stochastic process does correspond to the Cameron-McKendrick model in the limit of large population size. That goes back to a classic result by Kurtz. But it's much easier to think about deriving effective population size for this individual level model. Okay, so
wait, sorry. Can you just go back to that previous slide? So I'm just a little surprised that S appears on the top. So you're saying that the individuals sort of. Oh, okay. So these are each individual is an infected person, right? And so it's the fact that S is on top for that rate just means that the more susceptible people, the more.
Well, it's S over N, so they're meeting, like, infected people are meeting susceptibles in the meeting people in the population. You want to know how often they meet a susceptible person.
Okay.
Yeah, I think Trevor just answered the question for me, but really the important thing is the ratio of S over N. And so this is actually the per capita rate that an infection generates a new infection. And that per capita rate is proportional to the probability, S over N, that someone that is contacted is susceptible.
Got it. Thanks.
Okay, good. So the way I'm going to derive the coalescent rate is first of all, I'm just going to state what it is. This is it, equation number 6. And there are actually multiple derivations that we could do. Over the past few years, I've seen this derived in 4 different ways. And I'll show you 2 derivations. But first of all, this is what it is. It's similar to the Kieman coalescent rate, except now what we have is that the rate of coalescence is inversely proportional to the number of infected squared and proportional to f of t. F of t is incidence. It's the number of transmissions per unit time. And then if we put this in the canonical form and solve for effective population size, you get that the effective population size is equal to prevalence or number of infections squared over twice incidence. So to derive this, I do make a number of simplifying assumptions. So the first assumption is that once someone is infected, a host can't be reinfected or superinfected. So someone is infected once and only once. And if that weren't the case, then you might have a situation where multiple to a single host. And for this derivation, it's very important that a single lineage corresponds to a single host. Another assumption is that there's negligible pathogen diversity within hosts. So if 2 lineages occupy a host, for example, following a transmission, they'll coalesce almost immediately. And the third assumption is that there's a very strong bottleneck at the time of transmission. So very little pathogen diversity is transmitted from one host to another. So how good an approximation is this to reality? It really depends on the application and on what you're trying to estimate. I've applied these models a lot to HIV, where we know that basically all of these assumptions are wrong. However, they can be a good approximation depending on things like the sample proportion. So if you're sampling a relatively small proportion of population, they can be a good approximation. And also in the case of sexual transmission of HIV, assumption 3 is actually quite fair. So it usually is a very strict bottleneck in transmission. Okay, so this is the first derivation of the coalescent rate. It's similar to what we have in our 2009 genetics paper. And this is sort of a heuristic definition, so it's fairly easy to understand, but not that rigorous. So suppose a transmission occurs at some time t. Select 2 lines out of the entire population of infected individuals with cardinality I. And select them without replacement. And those 2 infected individuals are the ones that are involved in the transmission event, or one of those individuals begets the other. Okay, so the probability that both those lines are ancestral to some sample is the probability that a coalescent event happens, or it's the probability that there's a common ancestry within a genealogy. So that probability is hypergeometric. It's the number of ways you can pick 2 lineages out of the set of ancestral lineages over the number of ways that you can pick 2 lineages out of the number infected. Now, if you multiply that probability by the rate that all births happen, for example, in the simple SAR model, it's proportional to the number infected times the number susceptible, then we get something that simplifies to the coalescent rate I had 2 slides ago. Okay, derivation 2, this is something that I learned of very recently. Last year, Daniel Wilson and Bethany Dearlove published a model which relaxes a lot of the assumptions I had on the last slide. So this was based on a metapopulation model where each deme in the metapopulation corresponds to a single infected host. And according to their model, a deme can be colonized more than once, so that there can be superinfection. There's a non-negligible population size within demes, so coalescence doesn't happen right away following a there's a non-negligible inoculum size, so non-negligible diversity can be transmitted between hosts. And in a previous result, effective population size was derived for such a model in the limit of a large number of demes. And that derivation is actually due to a paper in 2001 by Wakely and Aliakar. This is the equation. I'm not going to derive this at all, don't worry. I do want to point out one thing about this equation, however. So if you make the following substitutions, you'll actually retrieve the coalescent rate from our 2009 paper. If you set the number of demes equal to the number of affected individuals, if you set the colonization rate to the per capita transmission rate, which is incidence over the number of infected, if you set the migration rate to occupied demes, so this would be the superinfection rate, to 0, if you set the inoculum size to 1, if you set the population size within hosts to 0, then the fixation index F converges to 1, and take my word for it that making all the substitutions, my coalescent rate will pop out of that. So in some ways, this is actually a more elegant derivation because it's showing that this is a special case of a more general model.
And can you use that framework to generalize, to relax some of the assumptions that you were making before?
That's something I'm studying right now. I think almost certainly yes, but that's something I'm still working on. So of course in Wakely and Aliakar in the original paper, they didn't consider situations where the transmission rate was changing through time. And another important issue is that in reality the pathogen population size isn't constant through time either. So for example, in HIV, it'll start close to 0, it will ramp up exponentially, and then it'll converge to a small steady state during chronic infection. And that it would be hard to take that into account with this model. So I'll just say that's something for future work. Okay, so now I'll give a couple of examples for simple epidemic models. So I'll derive effective population size for the Kerrick-McKendrick model. I'll show what effective size is for different phases of the epidemic. Effective size to the number of infected individuals. So first of all, for the Kerrick-McKendrick model, we can simply substitute in this equation F for incidence of infection through time. If we do that and solve for effective population size, what we find is that the effective size is equal to the number of infected individuals over 2 times the transmission rate times the proportion of the population that is susceptible. Okay, so early in an epidemic, the epidemic is growing exponentially, and the ratio S over N is approximately 1. And in that case, we can say that the effective population size is going to be proportional to the number of infected, proportional by a factor of 1 over 2 beta. So here's an example of that. In this case, I've simulated a genealogy from a birth-death process with R0 equals 2, recovery rate equals 1. I calculated the generalized skyline estimate of effective population size from the genealogy. And then the red line shows the number of infected individuals from the birth-death simulation divided by twice the transmission rate. And you can see it's actually a very good correspondence. And so consequently, it's really not a bad estimate for the number of infections through time during exponential growth to simply fit a skyline estimate, for example, a Bayesian skyline in BEAST, and then to estimate the number of infections as NE times 2 times beta, presuming that beta is actually known. So that's an example of where effective size is actually a very good proxy for the number of infections through time. Is there a good example where effective size is approximation? And there are. So shown here is a model where the birth rate changes rapidly through time. So in this case, incidence isn't just proportional to I times S, it's proportional to I raised to a power of 1 plus alpha. And if this exponent alpha is greater than 0, then the population will grow faster than exponentially. So birth rates are increasing. And if the exponent is less than 0, then the population will grow slower than exponentially, so birth rates will decrease. And if we plug this into our solution for the coalescent rate, we get something similar to what we had before, except now in the denominator we have the number of infected raised to a power of 1 minus alpha. Okay, so if we increase the exponent alpha, the coalescent rate increases. And this can lead to some counterintuitive results. So this shows a simulation experiment from our 2012 paper. On the left shows a tree generated according to exponential growth birth-death model. And the bottom left shows the skyline estimate, which again correctly reproduces the exponential growth rate in the population. And on the right, we have a genealogy which was generated from a population where alpha was greater than 0. So it was growing faster than exponentially. And if you calculate the skyline estimate for this genealogy, you find that the effective population size doesn't increase at all. It's basically flat. And the reason for that is very clear if you simply look at this equation. So the yes.
So what I don't understand in that picture is like the normal intuition is that if you have exponential growth, you get a star-like phylogeny.
Yeah.
And because things are kind of expanding very rapidly and coalescence happens all there's more likely to happen back at the beginning of the growth. Whereas it seems like if you're expanding faster than exponentially, you'd get something even more star-like, whereas that doesn't look like it's the case at all. And if you have any intuition there, that'd be really helpful.
Right. Well, I mean, that intuition that you just related is, I think, exactly what most people would think at first glance. And that's why I like this result so much, because it is counterintuitive. So really what's going on here, the sort of hand-wavy explanation for this, without referring to any equations, is that the population is growing so fast that it's sort of constantly coming out of a bottleneck. And if it's constantly coming out of a bottleneck, then the common ancestor for any pair of lineages has to be in the recent past.
Yeah, interesting.
And the non-hand-wavy explanation is that, well, if, for example, alpha equals 1, then you have I raised to the power of 0, and the coalescent rate doesn't depend on the number of infected at all. Okay, and in that case, this is, and in that case, the coalescent rate is sort of constant, and you would get a tree where most of the nodes are concentrated close to the tips, and that's what you have here. Okay, so I'll move on then. So all of this is nice in theory. Some people ask me if anything like this is actually likely to exist in reality. And my answer is, in the case of slower than exponential growth, I think yes. I think this is actually very common. So for example, sexually transmitted infections, a large body of research shows how they spread through heterogeneous sexual networks. And in a situation like that, the epidemic will hit people with very high contact rates first, and once those are sort of removed from the population, the growth rate will slow down. And that's reflected in a lot of non-genetic data. It's also reflected in the genetic data, I believe, because phylogenies of things like HIV are very, very star-like. Maybe even more star-like than what you would expect for exponential growth. And that's the expectation under the slower than exponential growth model. So this is a simulation example of that. On the left is an epidemic spreading through a homogeneous population, and on the right is an epidemic spreading through a population with a negative binomial distribution of contact rates. And green shows the number of infections through time. And it's very explosive growth, but it's also slower than exponential because the growth rate slows down very rapidly. And then if you look at the lineages through time for those two epidemics, in the homogeneous population, the lineages through time decreases gradually over the course of the epidemic, whereas in the heterogeneous case, the lineages through time stays constant for a while and then drops off suddenly. So that sort of represents a very star-like tree. Okay, so so far we've only talked about very simple models without structure, so every lineage in a genealogy is treated the same. We can only get so far with that, so the next step is to look at models that have some sort of structure or where there's some difference between lineages. So this of course, there's a very large body of research about this already in the context of geography and related to the problem of estimating migration rates between demes. So for example, Bierley and Felsenstein developed some structured coalescent migration rates, and more recently, LeMay has developed substitution models for estimating migration rates. The basic idea underlying both methods is that if there is very infrequent migration between populations, then if you have some discrete character at the tips of a tree that represents where a taxon was sampled, that character will be very highly correlated with the tree. And if there's very frequent migration between populations, there will be very little correlation between that discrete character and the tree. So what we want to do is similar to that, except we want to do it for an epidemiological model where that discrete character doesn't necessarily represent some spatial information. It might actually represent some clinical or behavioral attribute in the model. So I'll demonstrate this using a simple SEIR model. So according to this model, infected individuals progress from susceptible to an exposed state where they aren't infectious, and then to an infected and infectious state where they can transmit, and then they are removed. So to analyze a model like this with a structured coalescent, we first have to decompose this epidemiological model into 3 processes. So the first process is the transmission process, represented by this red arrow. This gives you a matrix-valued function of time, which tells you the transmissions from each gene to each gene. The second process is represented by the second arrow, which is migration, and this gives you a matrix-valued function of time g, which tells you the migration of a lineage, migration rate of a lineage from each gene to each gene. And the final process is the population size. So this is the population size within each gene, and it's a vector-valued function of time. So for this simple SEIR model, there are basically 2 states that a lineage can occupy. It can either be in a host which is in the exposed state, or it can be in a host which is infected and infectious. So this matrix would be 2 by 2, and this vector y would be length 2. All right, so the basic pipeline is to develop an infectious disease model, like the SEIR model, decompose it into these 3 processes, and then calculate a likelihood. And the way we calculate that likelihood is to model the state of a lineage as a continuous time Markov chain, where the time-dependent rates of the Markov chain depend on these 3 processes, f, g, and y. On the state of both lineages. So it's not the case that the coalescent rate will be the same for all pairs of lineages. And in contrast to previous structured coalescent models where a discrete state of lineages are simulated on a tree, we actually use a master equation approach. So we actually derive the probability that a given lineage I will be in each state k. So we solve these vectors pik for each time point along a branch. Okay, so the way those master equations are developed for the internal states of a tree are by tabulating the rate that different events happen that can change the state of a lineage. So, so shown here, I've illustrated the SEIR model and the sort of tree that you might get from such a genealogy. Dashed lines correspond to a lineage that is in a host in the exposed but not infectious state. And a solid line corresponds to a host who is infected and infectious. The first way that a lineage can change state is by common ancestry. So for example, an infected individual transmits and generates an exposed individual. And the ancestor is always in the infected state because only people in the I state can transmit. The second way that a line can change state is labeled with the nodes 1 on the interior of the tree. And that's where, going backwards in time from tips to root, a solid line becomes dashed. And the way that can happen is going backwards in time, infected individuals become exposed, because going forwards in time, exposed individuals become infectious. The last way that a lineage can change state in this model is a little bit harder to understand. So going backwards in time, an exposed lineage can also become infected and infectious. How can that happen? So that can happen because of incomplete sampling. So if we zoom in on this clade with 2 exposed individuals, and we consider that perhaps there is some individual who wasn't sampled, and that's the red branch I, then if we prune that red branch I out of the tree, we get the tree where an exposed branch becomes infected. So basically what's going on here is that in this original tree, we're missing the point where this individual was infected. And that's how the lineage. So what we've done is we've worked out how to actually calculate the rate that these 3 events can happen. And that allows us to ultimately calculate the likelihood of observing a tree. So the organization of the model is sort of as follows. For each branch in the tree, we have a vector, p, that tells us the probability that each lineage is in each state of the model at each time point. At each node, we also have a coalescent rate. So this is a coalesce. And then we also have this function theta. Theta is a survivor function. This gives you the probability that a coalescent event has not yet happened within each internode interval. And the way you solve theta is simply by summing up all of the coalescent rates for all pairs of branches and solving this differential equation. Okay, so the point I want to make is that once you have all of these things, you've solved all the lineage state probabilities, you've solved for the survivor function, and you solved for the coalescent rate for all pairs of lineages, then it's very straightforward to calculate the likelihood of a genealogy. It's just the likelihood of a point process, where you take the product over all nodes in the genealogy, and each term in this likelihood is the probability of observing that internode interval with a node that involves the observed pair of lineages I and j. Okay, so that's most of the hard theory. Fortunately, this talk is recorded, so you can go back and watch it however many times you need to until you understand it. So now I want to actually bring it back to something a little more applied. So the reason I went through the SEIR model is this is actually a very common choice for Ebola. This has been used in a lot of previous modeling efforts related to Ebola. Again, in this case, the exposed state actually corresponds to the incubation period. So we're assuming that there's no transmission during this incubation period. Again, this is a value that varies between Ebola outbreaks, but probably falls between 5 and 13 days. And in my analysis, I also assume that the infectious period lasts an average of 5.6 days. Also, in the case of Ebola,
Eric?
Yes, go ahead.
Question. So, with this model, if you didn't know ahead of time what this incubation period was, would you have any hope of pulling it out from just the genealogy? And you don't have the tips labeled with I and E, I imagine. Just from the structure, can you have any hope of seeing this versus SIR?
Basically, no.
Okay.
You need some other piece of information. If you can fix the growth rate in the epidemic from the other time series data, then it is possible.
Okay.
But it's quite hard to do that. I actually tried doing exactly that. However, as you may have noticed from the figure, there were only 5 data points overlapping with the phylogenies. And it's very hard to get a reliable estimate of the growth rate from 5 data points. Yeah, so I think if we had more sequences over a larger range of time, we could actually try that. But I haven't tried it with the currently available data. I don't think it's possible to get a very reliable estimate with the currently available data.
Okay.
And sorry, when you do get when you have one of these estimates that's a range, how do you deal with that?
There are a couple ways you could do it. I just did the simple thing, which was to repeat the analysis with 2 values.
Uh-huh.
Another way you might do it in a Bayesian context is to define a very wide prior. And that would sort of incorporate all of the uncertainty in that parameter.
Sure. Okay, thanks.
And I think either approach is valid. Okay. So first of all, how do we put this SEIR model into the sort of canonical format so that we can analyze it with the coalescent? Okay, so we have 2 demes, exposed and infectious. So the transmission matrix is mostly zeros because only infected and infectious individuals transmit, and they only transmit to exposed individuals. So they only beget exposed infections. Similarly, the migration matrix is mostly zeros because you just have exposed individuals progressing to the infected state. And this is the master equations. I'm not going to go through this in detail. I just want to make the following point. So this is the equation you would actually solve in order to derive the probability that a given lineage is in a given state at some time in the past. And it involves the terms shaded in green that show how lineages change state according to migration. The term in blue, which shows how lineages change state with transmission, and also the term in red, which shows how lineage is lost due to transmission. And a more economical way of showing this equation is, which also makes it more obvious that this is a continuous time Markov chain, is simply to put it in terms of a dot product with a rate matrix R. And this is how you can actually define the rate matrix R in terms of the epidemiological model. Okay, so for this very simple SEIR model, it's actually really easy to derive on paper what the transition probabilities of this continuous time Markov chain is. So, so the rate that a lineage in the exposed state goes to the infectious state will be equal to the rate that transmissions happen in the population, so basically beta times I. And the probability that a given lineage is involved in a transmission event is just 1 over the number of exposed individuals at that time point. Similarly, the rate that a lineage goes from the infected and infectious state to the exposed state is the rate that all individuals in the population progress from exposed to infectious times the probability that a given particular lineage is involved in that event, which is just 1 over the number of infected. Also, the coalescent rate for a given pair of lines is easy to derive. So that is the rate that transmissions happen in the population, beta times I. It's inversely proportional to the number of exposed times the number of infected, so just the probability that a given pair of lines are involved in the transmission event. And then this term in the numerator is the probability that the states of the lineages I and J are consistent with that event. So for example, the ability that lineage I is exposed while lineage J is infectious. In that case, lineage J can beget lineage I. Also, we need to know that the state of the ancestral node at a coalescent event is state I, because only I's transmit. Okay, so I'm actually going to finish my talk by pointing out something that we can learn from the genetic data that you really can't learn from the traditional surveillance data, so the number of cases reported through time. So this tree is the maximum posterior sample tree from the analysis by Andrew Rambo. And the thing I want you to see in this tree is that it deviates very, very strongly from a neutral coalescent tree. It's very, very imbalanced, and also the branch lengths are highly correlated. Neighboring branch lengths are highly correlated. So you have many instances where one branch length is very short and another branch length is very short. So why is that? We put forward the hypothesis that superspreading is what's generating those patterns. So before I talk about our hypothesis and our model for it, I would point out that another explanation is very, very strong natural selection, which can also produce very imbalanced trees. My co-author on the Ebola work is Sergei Kosakovsky-Pond. And by the way, Sergei has a very nice phyloseminar of his own. He actually has 2 philoseminars. And if you're interested in how he has done this analysis, I'd recommend that you see those. But he actually examined the sequence data for evidence of natural selection, and he did find some on the glycoprotein in particular. The glycoprotein controls entrance to host cells, and it makes sense that that would be under selection because the virus is adapting to a new host species. But this gene, glycoprotein, actually is a fairly small proportion of the genome, and most of the substitutions seen in the data set aren't involved in glycoprotein. Also, the time scale is very, very short, so this entire tree spans only several months. So I think it's very unlikely that natural selection explains the sort of imbalance that we see. So basically, I'm going to show you a model that allows us to estimate the degree of superspreading in this epidemic.
Right. Can you go back a step? What I'm back to the tree. I'm confused with when you say that the neighboring branches are highly correlated. So if this is a time-based tree and it's an ultrametric tree, and you have oh, this is not an ultrametric tree.
No,
I see.
But it is time-stamped, yeah.
Well, but I mean, like if you sample two people on June 1st or whatever, then they're guaranteed to be equal branch lengths back to their common ancestor.
All right. So I'll clarify what I mean here. I actually mean correlation between an ancestor branch and a daughter branch.
Ancestor. I see. Okay.
Right. So you see lots of examples where there's lots of short branches connected to each other.
Okay. That makes sense.
All right. Then I'll show you exactly why I think that's happening. And I'll also explain in a moment what the colors in this tree mean. Okay, but first of all, why might we be interested in estimating the degree of superspreading? So there's a lot of mathematical epidemiological work showing that if holding R naught constant and increasing variance in the individual level reproduction number, so increasing variance in the number of transmissions per host, the probability that a single introduction into a susceptible population will trigger an epidemic is lower, which is good. And the probability that an epidemic will die out due to stochastic effects is also greater, which is good. However, if an outbreak or an epidemic does happen, it's likely to be more rapid and more explosive, and that would complicate contact tracing efforts. It's also the case that in an epidemic with superspreading, targeted interventions are likely to be relatively more effective. So if you actually did have some way of identifying people who are at greater risk of transmitting, then it would certainly make more sense to focus on them. Okay, so here's a very simple variation of the SEIR model that has superspreading. So now, once people progress from exposed to infectious, they can either go to an IH state, where they transmit, or to an IL state, where they don't transmit. So with probability P, they progress to the IH state, and with probability 1 minus P, they progress to the IL state, followed by death. Okay, and so what this tree shows, I'll explain what the colors mean now. The red means that a lineage is likely to be in the IH state, and blue means that a lineage is likely to be in the IL state, so not transmitting. And the ancestor of a node is always in the IH state because they transmit. And it's also the case that when a lineage is red, it's more likely to undergo a coalescent event. This sort of model is actually reproduces the same sort of patterns that we see in this tree.
Wait, did I miss? There's a transition between the IH and IL states?
There's not.
So what does it mean when you have blue going to red then?
A host is in IH or IL. What you do is you solve for the probability that the host is IH or IL, and so that gives you a spectrum.
I'm not quite following. So, but it is through time. I mean, so when it's blue on the left, that means that they were in the IL state, and then they become in the IH state as they go right.
No, the way to read this is as a boundary condition. Actually, we assume that when someone is sampled, the probability that they're in the IH state is the parameter P. And then as we go backwards in time, we solve for the probability that the lineage is in the IH and IL state. And it's certainly possible for a lineage to jump from IL to IH by an unobserved transmission event.
Okay, that's what I'm, okay.
Right, so I mean, of course, we don't know who infected who, and we can't say that the lineage on the interior corresponds to the same person we sampled. Right, so it's certainly possible that it's actually easier to see for some of the longer branches. So here you have a red branch at the time of transmission, which gradually becomes blue. And that's because there could actually be a series of transmissions along this branch, and you don't know the state of the individual at the end of it. So what we're doing is we're actually calculating the probability that at the end of this branch, going backwards in time, that the host at that time point is IL.
But when you sample people, they're all in the infectious state and they're all showing symptoms.
That much is true, right? So I think we can say that with certainty. What we can't say with certainty is whether they're IH or IL.
Okay.
And unfortunately, you do have to make some assumptions in order to fit this model. And one of those assumptions in this case was that the probability of being IH was given by the parameter p that we estimate. And I think a better solution would actually be for each sample to estimate the probability that they are IH, but that would probably require much more computation. You can sort of imagine having a parameter for every sample taxon. Okay, actually, I'll come back to the parameter estimates, but first I want to point out that it's actually very easy to check that this simple SEIR model reproduces the same sort of imbalances that we observed in the data. So we can do that by simulating coalescent trees. And we can do that from both the simple SEIR model and from the model with superspreading. And then we can see if it actually has the same correlated branch lengths and the same imbalance. And this is also useful for establishing the identifiability of parameters. So once we've simulated a tree, we can try to re-estimate parameters and see if we can actually reliably estimate them. So the methods for doing these coalescent simulations are described in my 2012 paper. I'll just show you the results right now. So the tree on the left is a simulated tree under the median posterior parameter estimates for the simple SEIR model. So this is a model without superspreading on the left. And then the tree on the right was generated from the model with superspreading, also under the median posterior parameter estimates. And I think this actually makes a pretty good case that the tree on the right looks much more like the real tree than the tree on the left. And we fit both the SEIR model and the superspreading model to the data and compared them using Bayes factors, and indeed the model with superspreading is better supported.
What I'm used to with just thinking about superspreading is that it reduces effective population size because it increases heterogeneity of transmission of children, of offspring of a node, which goes to the kind of more ladder-like tree versus the more bushy tree. Kind of makes sense to me. Yeah, just kind of intuitively.
Yeah, and that is indeed the case. So it's definitely the case that as you increase variance and the offspring distribution, effective population size goes down. There are actually multiple ways you could observe that, though. So in this case, we're sort of implicitly doing that by with a structured coalescent.
Cool.
I don't have time to go into the results now, but we actually have a separate line of research where we have looked at the effects of changing the offspring distribution explicitly in an epidemiological model without structure. That actually exactly corresponds to a structured coalescent model with two demes, because you actually have enough degrees of freedom in the the superspreading model to make the variance in the offspring distribution whatever you want.
Mm.
So all you have to do is set the proportion of population that goes into the superspreading state, and then how extra infectious those individuals are, and that allows you to make both the mean offspring distribution and the variance in the offspring distribution whatever you want. And the coalescent rate only depends on the mean and the variance. Anyways, a bit of a digression there. So this is actually our parameter estimates for two of the four models that we fit, one with an incubation period of 5.3 days and one with an incubation of 12.7 days. So we calculated the coefficient of variation for these superspreading models. So it's probably around 4.1 to 5.4. And to put that in perspective, the coefficient of variation for a homogeneous model would likely be between 5. So this is indeed extremely high variance in transmissions. Okay, I'm running out of time, so I'll run through some quick conclusions. I've shown how pathogen sequence data can contain a lot of useful information that's useful for epidemiological surveillance, and it can also tell us some things that you can't get from traditional surveillance data, like who infected whom, or evidence for superspreading. My current work is sort of focused in the following areas. I'm developing more realistic models to account for non-negligible pathogen diversity within hosts, as well as in the inoculum. I'm also working on fast approximate methods to deal with large sample sizes. Both these issues are very important in my work on HIV. And I'm developing software. So all of the results I presented were based on this R package, Volz, that we have in development. I'd also point out that Alexei Drummond's group has implemented the Coalescent models in Beast 2. I have to thank Simon Frost, who's been very helpful in developing the Coalescent models, my co-author Sergei Kosakowski-Pond on the Ebola work, and Andrew Rambo for providing the Ebola trees. Thank you.
All right. Yeah, thank you very much.
That's awesome. So one kind of major question, and this is, if just from looking at the Geyer data, those trees are very sparse. So if there's not very much node support within the three major clades. There's kind of a few mutations that give you tips that are like a pair of tips or 3 tips or 4 tips, but you have there. And so I would have thought that the beast reconstructions will be telling you a lot. If you just take the tree from beast, it's the internal node structure is going to be largely reflective of whatever demographic model beast is using. And I think for that paper they had some exponential growth coalescent model. And so
actually they used a SkyGrid.
Oh, okay, SkyGrid. Thank you. Sorry.
So it's actually a fairly simple demographic model. I haven't actually looked at the effective size predicted, and it's a good question what it is. I wouldn't necessarily assume that the SkyGrid would show the sort of exponential growth that we get out of our models and that we know is happening in practice. Because, as we've seen, sometimes these effective population size estimates might not correspond to the number of infected. Yes. And especially early on in Sierra Leone, the epidemic dynamics are quite noisy. Yes. We do see some spikes in incidence.
So do you trees? Like, I think that there'd be a large amount of variation out of the beast trees for the same reason, for kind of the exact structure that comes out.
Yeah, there is. I mean, but that's reflected in the credible intervals for the node heights or the times of common ancestry, and it is definitely important to take that into account when you're doing a phylodynamic analysis like this, especially for this epidemic. So I think in this particular case, one would be tempted to just take a maximum clade credibility tree, for example, and fit your model to that. But because there's so much uncertainty in both the topology and the branch lengths, I think that would be a bad idea. And that's not what we did. So what we did in this case was to actually integrate over the posterior distribution of trees estimated by Andrew Rambo.
Okay, that's all.
Yeah, I was just curious. So the R package, what you do basically is you formulate your model, or it's already formulated there, and then you hand it some trees, and then it comes up with the estimates of the various parameters.
A bit like that. So what you do is you formulate the equations in matrix form. So remember, we have to have everything in this sort of canonical format of births and migrations and population size. Mm-hmm. And you can express that using strings as differential equations or simply as R functions. And you pass the likelihood function these these three processes, the birth process, the migration process, and the population size process, along with the tree, and it will calculate a likelihood. And currently it's left up to the user how to use that likelihood to fit a model. So you could do maximum likelihood pretty easily with Optim. For this Ebola analysis, I used the MCMC package, or actually a modification of the MCMC package, to do a Bayesian analysis.
Cool. Well, I think that's it for questions from our side. Let me just remind folks that the next talk is going to be Matt Hall speaking on Thursday, October 9th at 9 a.m. PDT, which I guess is 5 in the UK, right? And yeah, look forward to seeing you next time. Thank you very much, Eric, for a very excellent and very clear talk.
Thank you, Eric.
Okay.